Thanks, Modi. I tried to come up with a clever title that used the letters TBA, but I wasn't clever enough for it. I thought that was pretty clever. And I'm using chalk that I brought instead of chalk that's being supplied. I brought some of the Japanese full-touch chalk, but y'all should let me know if it's not readable or not, and I'll switch to the breakable kind. Before I start talking about ascent properties for CI dimensions, which is joint work with Tirdad Sharif, I want to just say a little bit about how I met and my relationship with Roger and Sylvia. So if I remember correctly, and I'm not 100% sure about this, the first time that I met Roger and Sylvia was in San Diego, the joint meetings in 1997. When I was a second-year graduate student, still working through a reading course in Etienne MacDonald, which does not include the words Cohen-Macaulay or Gorenstein anywhere in them. And I'm going to go to the commutative algebra session, and everything was Cohen-Macaulay this and Gorenstein that, and I was just totally frustrated. And so sitting at the back of the room working on my exercises for my reading course with my advisor, and Roger noticed me back there and came back there and introduced himself, and I just felt immediately very welcome to the community. And that's one of the things that I always like about Roger and Sylvia, is that commutative algebra is a very welcoming environment, and Roger and Sylvia are particularly welcoming and particularly kind within that. And I think that, especially with the world as it is nowadays, kindness is a wonderful thing. And so, thank you. So ascent properties for CI dimensions, you don't have an abstract to look at, so I can't give you the punchline right now. But what I want to do is I think that not everybody knows about CI dimensions, so I want to motivate that and then introduce it and then tell you a couple of things about it. So in my opinion, the story starts with the theorem of Auslander, Buchsbaum, and Serre. So let's let Rm K be a local ring, and by that I mean commutative Noetherian local ring, unique maximal ideal M, and residue field K. And then the theorem of Auslander, Buchsbaum, and Serre says that the following conditions are equivalent. The first condition is that the ring is regular, right? Which means that the Krull dimension is as large as possible relative to the number of generators of the maximal ideal, or the number of generators of the maximal ideal is as small as possible with respect to the Krull dimension. The second condition is that every finitely generated R module has finite projective dimension. Okay, so, and I'll put parentheses, so it's true with or without the finitely generated condition, right? If you have a regular ring, then every module has finite projective dimension. And that's equivalent to the version that I like better for non-finitely generated modules, which is finite flat dimension. And because the ring is local, those are equivalent. Flat dimension is just a little bit more nice for interacting with non-finitely generated modules. And then the third condition is that you only have to check the projective dimension of one module, and that's the residue field, right? So PD and that's equivalent to the flat dimension being finite, right? And nowadays, this is something that you see, in a first course in homological algebra, if you're lucky. But back in the day, right, the question of localization of the regular property, right, if you have a regular local ring, localized at a prime ideal, does the localization have to be regular, was a really hard problem. And the fact that finiteness of projective dimension localizes really easily allows you to solve that problem really quickly. So I always think of this as the real poster child for homological methods in commutative algebra. And so for other ring theoretic properties that one might be interested in, the Gorenstein property or the Cohen-Macaulay property or the complete intersection property, there are versions of this theorem. The one I'm interested in is the one for complete intersections. So this is a theorem that I'll credit to Avramov, Gasharov, and Peva, which says the following are equivalent. Condition 1, R is, and I'm going to be careful here, a formal complete intersection, right? Because we know that complete intersections are not necessarily complete intersections because of a paper of Dave with Ray Heitman. So when I say formal complete intersection, what I mean is that when I take the M-adic completion of my ring and write it as a quotient of a regular ring by some ideal, then the ideal I is generated by a Q-regular sequence. Right, which is just a little bit more flexible than actually asking that R be a quotient of a regular ring. So Q is regular here. And now I'll tell you what the punchline to this point is before I tell you the definition. So the condition 2 that's parallel to this is that every finitely generated R module has finite CI dimension, or CI flat dimension if you're thinking about modules that are not necessarily finitely generated. And I didn't say this out loud. The flat dimension, so projective dimension says I want a bounded resolution by projective modules. Finite flat dimension says I want a bounded resolution by flat modules. Okay. And I'll say what CI-dim and what CI-FD are in a second, but the third part is just like here, that the CI dimension of the residue field is finite, which is equivalent to the CI flat dimension of the residue field being finite. And so the definition of the CI dimension, also due to Avramov, Gasharov, and Peva, says that your module M has finite CIFD as an R module if there exists a diagram of local ring homomorphisms R to R prime coming from Q, let's say, where call this one phi, call this one tau. Phi is flat, tau is surjective with kernel generated by a Q regular sequence. Such a diagram is called a quasi deformation of R. So such a diagram exists such that when I take my R module M, tensor it up to R prime, consider it as a Q module, that Q module has finite flat dimension. Okay. Right. And so for instance, from this definition, right, if R is a formal complete intersection, then I can take R prime to be the completion. Q is my regular ring surjecting onto there, and because Q is regular, every module over Q has finite flat dimension, and so every module over R has finite CI flat dimension. there is a Gornstein version of this that's due to Auslander and Buchsbaum, Auslander and Bridger for the finitely generated modules, and Enochs and Genda for the non-finitely generated modules that has an exact same parallel property. And as with all the talks, please do interrupt me if you have questions. It's all good.
Okay, when you have a model of finite Gornstein dimension,
Yes.
you have a resolution in terms of totally reflexive model.
Yes.
Okay? What would be the analogous in this case? Having finite complete reflexive dimension.
That's a really good. So the question is, so in the finite projective dimension means that you have a bounded resolution by projective modules. G dimension means that you have a bounded resolution by totally reflexive modules. Is there a version of that for the CI dimension? And that's actually connected to an open question that I want to point out. So, question, if 0 to m prime to m double prime to 0 is exact, and 2 of the modules have finite CI dimension or CI flat dimension, must the third one have finite CI FD as well? So properties for projective dimension, definitely true, long exact sequence in extra Tor, if you like. Finite G dimension and finite G flat dimension, also true because there's a nice functorial characterization of those things. For CI flat dimension, it's a wide open question. And I don't care which of the two you choose, I don't know how to get the third one. And so now if you imagine that this, so the question of whether or not you have a resolution by totally reflexive, if you start with a bounded resolution by modules of CI dimension 0, the question of whether or not that implies that the module you started with has finite CI dimension is equivalent to this. The other direction is not hard. So if you have a module of finite CI dimension, take a free resolution, truncate it at the top, that module will have CI dimension 0 using the same quasi-deformation, but the other direction is wide open. Special cases are known. If one of the modules has finite flat dimension, then you can use any quasi-deformation to detect the CI flat dimension. And so this one, if and only if this one. But if all three have infinite flat dimension, we really don't know. I learned about this question from Sasha Gerko. It's around 2000, 2001 when we were in France. It's a frustrating question. And it really does hinge on, actually, I want to make this point. The difficulty with this problem is similar to the difficulty of the ascent problem that I want to talk about in a second, is that, so if I suppose that these two modules have CI flat dimension, there's a quasi-deformation for this one, there's a separate quasi-deformation for this one, and it's not clear how to combine the two quasi-deformations to get a single quasi-deformation that works for both. Right? And really that's the only reasonable way to think about, well, that I've found. And we can get approximately the result, but not the exact result. Yes? No, it doesn't have to. So the question is, if you have a module of finite CI flat dimension, you have a quasi-deformation that exhibits the finiteness of that. If you give me another quasi-deformation, well, I don't have an example off the top of my head, but I think that it's not true that you can see the CI flat dimension from any quasi deformation. So you really would need to find some way to fuse the two together. And some work that I've done with Said and Assay, we have some ideas in some cases about how to fuse together the flat parts of the quasi deformations. So we can we've got a diamond diagram, but the deformation parts, we don't know what to do with. It's a frustrating question for sure. Other questions? These are all good questions. Good. So the ascent question that I'm interested in, so let's let RMK to SNL be a flat local ring homomorphism, and we'll let M be a finitely generated S module. And now I'm going to state a very general version of this, which is under what conditions does the finiteness of HDIM over R of M being the finiteness of that imply the finiteness of HF, I should have HFD up here, and down here HDIM over S of M. So I've got a module over the target ring. I'm interested in when it has finite. So HFD could be just the flat dimension or the CI flat dimension or the G flat dimension. And I want to know what conditions allow me to ascend the finiteness of those homological dimensions from the base ring to the target ring. And the answer is not usually. So you need some conditions on the ring homomorphism in order for this to even be a reasonable question because of these theorems here, right? So if you start with a field down here, well, everybody's got finite projective dimension over a field, but this ring can be all sorts of crazy, non-Cohen-Macaulay, right? And so the question of the ascent of there sort of depends on, and at least this is the philosophy that we have, is that if you should expect the corresponding ring theoretic property to ascend, then you should expect the corresponding homological dimension to ascend, right? So for instance, if the closed fiber of this ring is regular, then R being regular implies that S is regular. Yes.
Based on your question,
Yes.
that the third part of three frequency there, you cannot ensure that the complete second dimension of the maximum ideal is finite. You cannot.
Yes.
So
Wait.
is there any torsion free test in all this system?
So sorry, I guess I misunderstood your question. Because the maximal ideal is bridged to the residue field by a free module. So that free module, you can see the CI flat dimension from any quasi deformation. So this will be finite if and only if the CI dimension of the maximal ideal is finite. Yeah. Other questions? Dave? Okay. Okay. Okay, great, great. I figured that examples would probably abound. Other questions or comments? Good. So, since the regularity property is linked to the flat dimension, right, the corresponding homological dimension version of that theorem says that, and this is due to Avramov and Foxby, says that if the S mod MS is regular and FDRM is finite, then FDSM is also finite. And they actually have the converse to that result as well, and they have nice bounds on the actual values of the flat dimensions over R and over S. Okay. The descent question is actually, this seems surprising to me, seems to be the harder of the question. So I've stated the ascent question here. The descent question just says, if this is finite, when is this finite? So for instance, the Gorenstein version is due to myself and Shrikant Iyengar. We don't know in generality the descent question answer for G dimensions. So we know it in the case where R has a dualizing complex, and using new techniques that I developed with John Todashek, I can actually deal with the case when R has Gorenstein formal fibers. But I don't know what to do in the general case about the descent question. Good. So what I want to talk about for the, wow, I have a lot of time left. This is great. So apparently one of the rules is that this is math that we shouldn't be doing in public. Sorry. So I'm going to show you some technical details of a proof of the version of the complete intersection version of this that I do know. It uses one of my favorite tools, which is the Kazul complex and the derived category. So the theorem, which is due to myself, I'm not used to putting my initials first, and Tirdad Sharif, is that if R to S is essentially a finite type, and flat with S mod MS flat and local with S mod MS formal complete intersection. And so just because I can, I'll state the version that I know. So I'm going to, I'll state two versions. So version 1 says that if M is a finitely generated S module and the CI flat dimension over R of M is finite, then the CI flat dimension over S of M is finite. And then part 2 says that if N is a finitely generated S hat module, then I get a similar implication. So these are the two cases where I can actually ascend the complete intersection flat dimension. So essentially of finite type or essentially of finite type. And I'm not ashamed to flaunt my ignorance. The descent problem for complete intersection, flat dimension, even for the map from R to its completion, I don't know how to descend the property in general. That's banging rocks together. Good. Now, each of these pieces uses a stupid amount of technology in order to prove. You would think that it wouldn't be that hard, but the problem is that you start with a quasi-deformation for R, and you have to produce a quasi-deformation for S, right? And yes, flat, local. Yeah, it's sort of all squished in there. Yeah, flat and local. Thank you. Other questions? So I'm not going to talk about the proof of this part. Both parts are technical. One of them I find a little bit prettier than the other, so I'll focus on the one that's a little bit prettier. But the point here is the essentially a finite type condition guarantees that when I have a map, my flat map going out of R to make my quasi-deformation, that when I tensor these two maps together, I get something Noetherian, right? And that's the first technique. That's how I start to build my quasi-deformation over S, okay? And there's a diagram. All right, aye. Mm-hmm. Geez, I would love to know something like that. I don't know. Yeah, a quasi-deformation-free characterization of CI dimension would be really nice. And there are approximations of that. So one thing that I didn't say is that your modules of finite complete intersection dimension have polynomial growth for the Betty numbers. And that's what Avramov informed me was one of the main reasons for doing that project was to find interesting classes of modules that have that property. Right? So they have polynomial growth on the Betty numbers and their finite G dimension. And so Gerko has a homological dimension that's built out of those two conditions. And that one you can do lots of things with because those conditions play well with short exact sequences, for instance. It's been suggested, and I don't know, Dave, if you've followed through on this or not, but using the cohomology operators in order to understand things a little bit more finely than just understanding the sequence of Betty numbers. I think that would probably also behave well with respect to some of these operations. But a strictly sort of vanishing of extra, vanishing of Tor characterization, I don't know. Other questions? So I want to assume part one and show how to use it to bootstrap my way up to part two. And there are a couple of technical difficulties with this so my diagram R to S hat, right? So this is flat and local with a CI closed fiber. This is, of course, flat and local with an incredibly nice closed fiber. And so I have my N, which is an S hat module. It's finitely generated. And I'm going to assume that it has finite CI dimension over R. And so what you might want to do is to say, well, part A says that CI flat dimension finite here, tells me CI flat dimension up here, and how hard can it be to pass to the completion, right? And so the very first thing I said is the thing that's most wrong, is because part one assumes that my S module is finitely generated. And if I have a finitely generated S hat module, chances are better than not that it's not going to be finitely generated over S, right? And so you have to do, in order to even invoke part 1, you have to do something in order to turn your given module into something that's also finitely generated over S, right? And this is where I have to sort of spread my wings a little bit and use a Kazoo complex and actually start doing these things for complexes instead of just modules. The good news is that the symbols don't change. Well, they change a little. I won't change them. So one can do all of these constructions for complexes instead of just for modules. So CI-FD Rx makes sense for any homologically bounded R complex. And again, I'll just write R prime Q FDQ R prime tensored over R with X being finite, right? So I have a chain complex here. I tensor it along my flat map, so I don't have to use derived functors here if I don't want to. And then asking whether or not that has finite flat dimension over Q is just asking whether it's equivalent to a bounded complex of flat modules over Q, which is the equivalent to the version that I stated before for modules. And if you're like me, you're on the lookout for sort of cute extensions of things that don't actually give you something new, but allowing this little bit of flexibility actually allows me to transform my given module into something that's going to be finitely generated over S. And that uses the Kazoo complex. Which I have a little bit of time, so I'll say a tiny bit about. The Kazoo complex, if y'all don't know the Kazoo complex, then let me preach, because it is pretty much my favorite tool right now. Is if I've got a problem, I will just hit the problem with the Kazoo complex, and frequently it's sort of smoothed things out really nicely. So let me explain how. So Kazoo complex on over R on one letter A is just the complex 0 R R 0 with multiplication by A in the corresponding slot, and I'm indexing things, if you want to keep track, homological degree 0 and homological degree 1. And then Kazoo complexes on longer sequences are obtained depending on your preferences, either by tensoring short ones together or by taking iterations of mapping cones. So KRAB looks like Pascal's triangle with the A B matrix here and the B minus A matrix here. And everybody's got their sign conventions that they use. The signs here have to be different from the signs here, right? So that you actually get a chain complex that is a chain complex because of the commutativity relation between A and B. Okay. And so I will just call KR equal to KR x1 up to xe, where x1 to xe is a minimal generating sequence for maximal ideal. And similarly for KS and KS hat. And the really pretty thing about this is if I take K, we'll do KS tensored over S with my module N, say. So that's now a chain complex, and so what I've done is I've replaced my R's that I have here with capital N's, right? And so I have 4 copies of N here. So that's going to be a bounded complex of copies of N. So each of those modules is finitely generated over, I want S hat here. Going to be finitely generated over S hat. But because I'm using a generating sequence for the maximal ideal of S hat, the homologies for this are all generated by, annihilated by the maximal ideal of S hat. And so those homology modules are finitely generated over S hat, annihilated by the maximal ideal of S hat, which means that they are finite dimensional vector spaces over the residue field of S hat. Finite dimensional vector space over, right? The residue field of S hat is the same as the residue field of S, which I called L before. And here's what makes this whole thing work, right? Same residue field means that these modules are also finitely generated over S. So now what I've done is I've taken my given finitely generated S hat module, I've had to sort of flatten it out a little bit with the Cazul complex. It's got homology in a variety of degrees, possibly from 0 to E, depending on how naughty my module N is to start with. But the homology modules for that are finitely generated modules over S, and the hidden version of part 1 here, it also works for for complexes such that the homology modules are finitely generated over S. So the sequence here, I have my Ci flat dimension over R of M being finite. It is a very, very special case of the short exact sequence property that allows me to conclude that the Ci flat dimension over R of that Ks hat, tensored S hat, N, is finite. And then my part 1 tells me that the Ci flat dimension over S of Ks hat, tensored over S hat with N is also finite. Right, so I've overcome the first obstacle, which is the lack of finiteness over S, which was preventing me from invoking part 1 in order to ascend directly my property for N. Now I have to deal with the fact that I've twizzled with a Cazul complex here. Okay. See, I wasn't raised by Roger, so I don't think I used the right verbs. Is twizzle an acceptable verb? Okay. And I didn't see it on the list during Iowa's talk, so great. Good. Yeah, it's T for twizzle, right? It's the only reasonable verb. Now what one has to do is one has to use a little bit, and I'm going to, because I've got 35 seconds left, sweep a little bit of information under the rug. The fact that this is a particularly nice complex already over S hat allows me to ascend so base change so if I base change with a flat extension, that property works just fine, okay? And then the thing is because this was already homology given by finite dimensional L vector spaces, this base change complex is actually the same, homologically considered, as the complex my intermediate complex there. And now, nowhere yet have I, well, okay, that's a lie. Never mind. Scratch that. It is a property of finitely generated modules that says if I tensor with a Kazoo complex and get something of finite CI flat dimension, then my original thing had to have finite CI flat dimension. So. Which is what I wanted. And I will tell you that there's a tiny bit of lies up here that this isomorphism that I have is correct, but it is not, at least not as far as I can tell directly, respecting the entire S hat structure. It respects the S structure, but I have two S hat structures on this complex, and the left one and the right one don't agree. And so there's another technical thing that I have to do which uses local cohomology for complexes in order to actually trade this complex for a derived local cohomology in order to allow that. But I see everybody's eyes glazing over, so I'll stop here. Thank you. So it's not the Zeroth homology. That's a great question. Yeah, right. So I wouldn't actually know how to get the Zeroth homology. But the thing is, so if you follow, so S hat comes equipped with a quasi deformation, right, that can see the finiteness of this complete intersection flat dimension. And now the thing is that I can take that Kazoo complex and I can push it along my quasi-deformation, the flat part, and then lift it back along the deformation part. And now it's so there's a result of Ramov and Foxby that says that as long as I've got at least that much control, then the flat dimension of the tensored thing being finite gives me the flat dimension of the original thing. And it's absolutely, the things that are crucial are that this one has a finite projective dimension and that this one is finitely generated. Both of those are absolutely crucial for that. Yeah. It's actually the maximal ideal itself, because I used a full generating sequence for the maximal ideal. If I'd have just used a system of parameters or generated an n primary ideal, then I would have to use a power of it. And the argument would still go through just fine. Well, they're finite dimensional vector spaces. I mean, they might have rank, right? Yeah, but they're direct sums of simple modules, yeah. The homology modules are. But you can't take those apart, right? So this, and that's an important point, this complex has finite CI flat dimension, and its homology modules are finite dimensional vector spaces. But that doesn't mean that the individual sum ends of the homology modules have finite CI flat dimension, because that would imply that S hat would have to be a complete intersection. So the way that they're actually braided together is important.